this. Just put the thing on full screen. Should be fine.
Okay, take this.
Yeah, this
No, it doesn't appear.
It doesn't hide this very stupid thing. You can put on top or whatever.
Yeah.
Maybe you can extend your screen.
Mm-hmm.
Probably not. Oh, yeah, you'll stop. Maybe just go back to the previous setting. Should be fine.
Welcome to today's TITAN talk. I'm Yin Qing, I'm the organizer of this TITAN series. Today we have Homayoon, and his topic is automatic meta descents. Let's welcome the speakers. Thank you.
Welcome, everyone. Thanks for coming. My name is Homayoon. I'm going to talk today about automatic meta descent. Yes. How about now?
You get it as tall as you are, yeah. Not easy. Oh, yeah, keep going.
How about now?
It's good to stand as you're talking about.
Is it okay now? Okay, cool. So online continual learning agents should be able to track non-stationarities in the environment. In the real world, the world changes, and we want our agents to be able to adapt to changes in the environment. But the environment can have both stationary and non-stationary components. Some parts might be changing all the time. Some parts might be stationary. So it's a good idea to have a separate step size for each weight of a neural network agent. And this way, if some weight needs to change quickly, then the step size can go up to track the changes, and if some weight needs to stay stationary, the step size can come down so to reduce the error, the online error that is caused by that weight. So this is the problem of step size adaptation, and one solution to it is meta descent, which we are interested in. In meta descent, the step sizes are updated to optimize the same objective as the main objective of the problem. So both the weights and the step sizes are optimized by gradient descent to minimize the loss of the problem. And then, so let's look at to make an example, let's look at a non-stationary task. It's inspired by the incremental delta bar delta task. But instead we're using a neural network which has one hidden layer of sigmoid activations. It has 10 hidden units, 10 inputs, and 1 output. And then we have, we're using mean squared loss, so it's a regression task. There's a learner network and a target network. The learner has to approximate the target. And there are 10 output weights for the target and for the learner. They have the same architecture. I split those target weights, output weights into 2 groups of 5. One group is initialized to either +1 or -1, and the other group is initialized to either +100 or -100, and in a different setting of the same task, they're initialized instead to +1000 or -1000, so they have different magnitudes. So these are 2 problems, 2 separate problems. One is low magnitude, 100, and one is high magnitude, 1000. And then since it's a non-stationary task, we're flipping the signs of 2 output weights every 50 steps, one of each group. So one from the low magnitude, one from the ones that have magnitude of 1, and one from the ones that have magnitude of 100 or 1000. We flip the sign. And then, yes?
Could you say what you mean by the third bullet? What are the target output weights that are split into 2 groups?
So we have a learner, we have 2 networks. One is learner and one is target. They have the same architecture. Both have 10 inputs, 10 hidden units, and 1 output, which means that there are, at the last layer, the linear layer, there are 10 weights.
Well, the output weight, so
Yeah.
the last layer.
Yes. So target output weights is the last layer, which is linear layer. Yeah, so we ran SGD, Adam, and stochastic meta descent. It's an existing meta descent method on this task. And these are the results. So these are sensitivity curves. The x-axis is the step size or the meta step size, and the y-axis is the scaled mean squared error of the regression task online 1 sample at a time. And then they're averaged over 10 runs. So what we can, lower here is better. So what we can see is that SGD and Adam can't do as well as SMD, especially in the low magnitude case. So which shows that meta descent in particular is needed for non-stationary tasks to be able to adjust step sizes online. And then and then if you average between the 2 tasks, between the solid line and the dotted lines, you get the curves on the right, which means if you try the same algorithms on different problems, this is the average performance that you would get on different problems. And this is caused because the best hyperparameter settings are very different for SMD as compared to, say, SGD or Adam. And this is a problem. This means that every time we want to try SMD on a new task, we have to tune its meta step size to very different values every time. And this one, the curves that I just added that achieve very low error is the method very similar to the one that I'm going to introduce, but this shows that if you have good meta descent methods, they can perform well and they can not need the need to tune the step size every time for every problem. So we take inspiration from Adam, which has been shown to be robust across different problems. This is results from a paper by Schneider et al. They show that here, for example, the blue curves are SGD. These are against sensitivity curves, and higher is better. And the 8 figures are for 8 different problems. And you can see that for different tasks, you have to tune the step size of SGD and then to be able to achieve the best performance, and for momentum a bit less maybe, but for Adam, except for the first problem on the top right, for the rest pretty much you can just set the step size between 10 to the negative 4 and 10 to the negative 3 and get near best performance. So what does Adam do? And can we extend the ideas to meta descent? These are the update rules for Adam. Title says autumn, but it's not autumn yet. These are the updates for Adam. So we have M and V. M and V are two statistics of exponential moving averages of gradients and squared gradients that you calculate on every step. And then we compute this quantity Z, which is the first moment divided by a square root of the second moment, and then use that Z instead of the gradient for the weight update. And now for autumn, we can apply something similar. The main update, what the step size update uses instead of gradient is the quantity in red. It's the step size alpha, which is a vector, times Z times the gradient. And then what this is basically doing is, Z is basically a statistic of the direction of past gradients, an accumulation of them, and then if we multiply it by the gradient, delta L, and if they have the same sign, it will lead to an increased, it will increase H, and if they have the opposite signs, it will decrease H. If it increases H, it will increase rho on the first line on the top left. And if it decreases, it reduces rho. And rho is basically a log of the step size. So if you have a lot of variance in the gradients, it will reduce the step size. And if you have the same signs over and over again, it will increase the step size to make it go faster. That's the basic idea. And then, so what I mean by applying the same ideas of Adam is applying the same, computing the same statistics. So we take the quantity in red and then apply the same exponential moving average and exponential moving average of its squared quantity. And then use those computed statistics to apply to the step size update. So I ran SGD, Autumn, and Adam on Hopper, the environments from Jim. I tuned beta 1 and beta 2 to a combination of 20 different values, and then for Autumn I tuned the initial step size and beta 1 and beta 2 to 18 different values. So in total, we tried more hyperparameter settings for Adam. And then you can see here that Autumn learns faster than Adam. And then in this particular case, the settings for beta 1 and beta 2 for Autumn were both 0. So I thought maybe this is a one-off thing, and if we try more commonly used values for beta, what would happen? I did get the same thing. So meaning that still Autumn learns faster than Adam. So another important thing was to compare the sensitivity of these two algorithms in terms of the step size or meta step size. On the left we have Adam, and for it, there's always a peak for all different hyperparameter values. Now these every point in these plots is now the average of run with a particular hyperparameter setting. And then for each hyperparameter setting, you can see that the step size around 3 times 10 to the negative 4 seems to perform best, regardless of beta 1 and beta 2. And the curves that are, like the red one at the top left, the curves that are not showing up is because those are the cases where beta 1 was much larger than beta 2. On the right, we also see the same thing, which is a good thing, which means that for most values of beta 1 and beta 2, we don't have to worry about it doesn't change the best meta step size too much, so we can use the same meta step size with different. These are both on Hopper. Yes, it is. It isn't. It is. I mean, we didn't change the environment, but because we're using an RL algorithm and we have actor and critic, and they change it at the same time, it changes the targets for both, so it becomes a non-stationary environment in the end. So I also wanted to, since we have two optimizers, one for actor and one for critic, I wanted to see if the improvement that we're seeing is just because we can, if we can have the same improvement just by setting different step sizes, just using Adam, but setting different step sizes for the actor and critic. So then I can plot the sensitivity curves, but using Adam. The blue curve is if when we're using the same step sizes for both actor and critic. And the orange curve shows the performance for that particular step size for the actor, but the critic was tuned to its best step size. So if you have a small step size for the actor, if you tune the step size of the critic, you can still improve the performance to some extent. And then if you do the same with critic, now for the green curve, the critic is shown on the x-axis, critic step size, and the actor step size is tuned to the best. So overall, it shows that probably critic step size is more tolerant of larger step sizes than actor, and actor is more tolerant of smaller step sizes. But the best performance is achieved when these step sizes are very close. And the best values that I found was for actor, I think, was 3 times 10 to the negative 4, and for the critic was 10 to the negative 3. So not that much of a difference between them. And then there might be some improvements, but in this case it's not significant if you tune them separately. But for Autumn, You can have one meta step size, and you can get the performance better than just tuning step sizes separately for Adam. Yeah, so that concludes my talk. Thank you for listening.
Time for questions. Rich.
I might have been walking around at the very beginning. Can you say again what question you're trying to answer?
So the first question was if meta descent is necessary for non-stationary environments, can we just use Adam and forget about meta descent? I think that's not true. We can't. We need meta descent.
So is Adam meta descent?
Sorry. Oh, so the first question was, do we need, for step size adaptation, can we just use Adam's adaptive step size, or do we need meta descent, where we have to learn individual step sizes?
Sorry, I came late. The train was not on time. But are you basing your conclusions on this one set of experiments with Hopper, or have you tried a bunch of different environments to see whether this claim you're making holds in more than the particular case and with a particular version of PO something or other that you're using? I'm just wondering how general
Yeah, so
your claims.
I didn't include those results. I also did experiments on 3 different variations of permuted MNIST, and I tried with soft actor critic on reacher environment and with PPO on Hopper again. So these curves show the average between those tasks, and then so it shows that Autumn is almost as robust as Adam. There are, of course, more experiments to run, but I did try different environments, and so far it seems good.
So I want to understand the algorithm a little bit more. Can I summarize the algorithm as you have a meta descent algorithm, and then for the meta update, you're applying the same thing. You're basically applying Adam to the meta update. Would that be a way of?
Yes. There are different ways to derive the step size update. The way we have done it was to assume that we're using the Adam's weight update.
So you're assuming that you're using Adam as the inner algorithm, and then your meta update basically differentiates through Adam.
Yes.
So jumping back to the problem setting, we're talking about non-stationary environments, and you kind of started by stating that if this is what we care about, sort of a non-stationary environment, where some parts of that environment are going to be changing very quickly, and other parts are going to be changing less quickly, or perhaps not at all, then what we should do is we should try to track the ones that are changing faster. We should have like a higher learning rate to track those faster. It seems like there's a really small gap there that isn't quite filled in my mind of, because we're going to use like deep neural net. Is this only, sorry, first I should ask, is the meta part of changing the step size only in like the last linear layer, or if we had a deep neural network, would this work through like all the parameters of the network?
So this algorithm works for all parameters.
So then what would be unclear to me is like if we have a deeper neural network in those intermediate hidden layers, it seems like things there would, some of them would be changing more frequently and some would also be changing less frequently. But I don't know exactly how to ask the question I'm trying to ask. But it seems like there's sort of a gap between the idea of things changing in the environment and us changing the learning rate of specific features that we might be tracking. Perhaps maybe the gap is like whether or not features are actually capturing these things that are changing or not. Does that kind of make sense?
So, yes, I think we assume that the weights that we have are representing the real world, and when some parts of the real world change, and the corresponding weights in the agent have to change. I think we're assuming that.
Yeah. So I want to believe that assumption holds true. It seems likely, but also it is an assumption, right? That's what I wanted to, yeah. Sure. I'm kind of just trying to work out my own thoughts.
Just really to follow up on that, like, but what's the alternative? So something changed, the agent has to track. That implies that the agent can only track by changing component of itself.
Yeah, I don't think it's, my question was less so like we shouldn't be doing this and more so I think, can this be formulated in a way that makes it clear? Like the tracking seems, I think I thought about this more since like Alex's last presentation, it seems just very like an unclear term. Yeah, it feels like the problem could be better specified, I think.
Could you show the entire algorithm again? I just don't quite get the variables. Like all these updates belong to your algorithm?
Yes.
And what are the, I sort of understand the right-hand sides, they are Adam's update. And what are the left-hand sides updates?
So I should go through derivation. So rho here is the log of the step size. And the step size is, we get the step size by doing exponential of this. This is what we want to derive. We want to derive an update rule for rho. And so we want to take, and we want to update it by gradient descent. So we want to take take a step toward the negative of the gradient of the loss with respect to rho. And then then we do chain rule, do gradient of loss with respect to weight times the gradient of weight with respect to rho, both of which are matrices. And then this inner quantity gradient of weight with respect to the rho, then we have to compute. Instead of the weight, we put in Adam's weight update, which is W minus alpha Z, as shown on the second row on the right. And then here we ignore the effect of alpha on the previous weights and the effect of alpha on Z. And if you do that, then you get, the matrix becomes a diagonal of alpha times Z, negative of that. And then if you plug this back into the above update, you get this step size update rule. And then we add Adam's running averages on top of this.
I see. Thank you.
Yeah, of course.
We have time for one more question.
Yes.
Thank you. This last slide made it more clear, I think, in my mind, as to what you were doing, which is trying to get rid of these hyperparameters. So how close are we to the hyperparameter-free algorithm, or is this it? Like, what remains to be done?
Okay, so we do have the 5 experiments that I showed, and on average, it seems that Adam is performing as well as, almost as well as Adam, and then is more robust to the meta subsize. What remains is to try it on more gym environments. I only tried it with PPO and Hopper, and then I also want to try it with other environments, gym environments, and real robotic environments in the real world, and with soft actor critic as well. Those are the things that right now come to my mind. Do you have any recommendations?
Just more broadly than the specific instances, what would you want to know? When would this field be solid? Let me put it this way. If you could ask a genie, can you answer this question? Because I have this question about my thing. What would that question be? You wouldn't have to do any work. The genie would answer.
I think we can maybe keep the conversation after this. And thank you all for coming today. Thank you.
Genie has to fly with the question.
Hey,
Hey.
I want to just give some advice about giving your talk. Your voice is not very strong.
Yes.
Okay, so, I mean, one thing is you can try to speak more clearly. But also just recognize your voice is not very strong. And so what you can do instead is put on your slides like, sentences, words. Like here, there are no words. And the words there are tiny, they're not readable, they're not very thoughtfully selected. Okay? Think of like putting down like what the message is. And then if you don't say it exactly right, if I don't hear it because my ears aren't very good, because I see the message.
Right. That makes sense.
I think you should try that. I mean, your slides are notable because you have almost no words.